Today we have brought another edition of ScoreBooster chemistry lecture, and our lecture today is going to be on electrode potentials. We discussed last time on electrolysis, because after electrolysis, the next thing that should be taught, that should be understood, is the application of electrolysis in our homes and somehow in our industries. Because basically last time we were talking about electrolysis, we discussed the application of electrolysis in three major aspects. We said in electroplating, in refining and purification. We did that. There are some other areas where we can apply electrolysis apart from all this. So that's what we want to discuss today, and the knowledge of electrolysis will guide us in all these areas. Our instructor is going to be Latif as usual. So at the end of today's class, we should be able to identify what is called an electrochemical cells. We should be able to mention examples, then possibly applications of electrochemical cells. Then we should be able to understand what is called an electrode potential. Then we calculate the cell potential. You see, I have cell rays and equations. I believe we are familiar with this block diagram that I put here. This diagram shows a circuit that contains a battery and connecting wires with this rod together with a bulb, so that when the cell is closed, this bulb lightens. Bulb lightens because we have flow of electrons from the negative terminal to the positive terminal of the battery. So it is the flow of these electrons that constitute what is called electric current. So now, and don't forget that we discussed about electrolyte and electrode in our class on electrolysis, where we say when we have a solution that contains movable ions, that this movement of ions can constitute what is called electric current. So if we have a solution that can do that, or we have substance in molten form that can do that, we call all those substances, we call them electrolyte. And the process of doing that, there's decomposition, then electricity pass. That is what's called electrolysis. So now, in a particular cell, when we have a cell, we have a solution that contains ionic, a concentration of ionic solids. So when we connect a metal, or it can be two different metals, or it can be or it can be any type of metal. I try to connect it and connect wires like that. We try to connect the bulb. So instead of this battery, what I'm trying to say is instead of this battery now, we can put a solution here, solution of ionic solid. The solution of ionic solid now will now serve as the source of movement of ions. So bulb will lighten up. So that cell contains what is called electrolyte and the electrode. So those metals that were dipped inside the solution are called electrodes. So through those metals, electrons are able to pass. So the type of cell that allow electricity to pass are called galvanic cell or voltaic cell. Volts from the voltaic cell or galvanic cell. So there are two basic types of voltaic cells. The first one is the wet cell, and we have a dry cell. So let's take them one after the other. The wet cell. in the wet cell, it is like that arrangement that we had during electrolysis. In the wet cell, we have two separate compartments. Each of them contains different electrodes and different electrolytes. In the first one, if let's assume that in Daniell's cell that we are taking as an example, we have copper cathode and we have zinc anode. So in the copper cathode, there's a solution of copper compound. In zinc anode, there is a solution of zinc compound. So when we now have these two compartments now linked together with another substance, a porous substance, the aim of this porous barrier is to prevent the two solutions from mixed together. That is, if we have the same compartment. So if we have different compartments, we can have what is called a salt bridge, like a bridge that links two parts of roads together. So now when we now have two separate compartments, we can have a salt bridge. Salt bridge also contains ions because we want the electrons to flow so that the circuit will be connected together. So if we are not using something that contains ions, electron will not flow from one compartment to another. So we have that's what we call salt bridge. Salt bridge. So the positive aspect of the salt will go to the negative aspect of the electrode, then the positive, like that, and vice versa. So when we have that, there is going to be electron movement from the negative to the positive aspect. The electron will move, only that the solutions will not mix together. That is what is called a salt bridge. In a salt bridge, you can have ammonium chloride, you can have ammonium nitrate in the salt bridge. But in these separate compartments, as I've explained, the solution of the compound that makes up the electrode is what is used. If you are using a copper electrode now, you make a solution of copper compound. If you are using a zinc electrode, you are making a solution of zinc compound. That is what we are saying. That is what is called a Daniell cell. So in the Daniell cell, there is a redox reaction take place. I remember we have solved the question on this before. So there is a reduction takes place in Daniell cell. So in that Daniell cell, there is an external circuit, that is the wire that link together the two electrodes from the outside. Then we have the electrodes, the copper and the zinc. So there is oxidation of equation. The reaction occurs in one of them, then the reduction in the other. That is redox that we are talking about. There is oxidation because there is anode, that is zinc. Is zinc in a zinc compound solution, so there's going to be a loss of electron from there. Zinc electron will be reducing. Electron will be moving from that compartment through the salt bridge into the compartment where there is copper electrode. Copper electrode now gain copper ion in the electrode, in that solution gains electron that flow from the zinc, so the copper now becomes solidified in that place. So as the size of zinc is reducing, the size of copper is increasing. So at a point in time, the two of them will be replaced because of obvious reasons. The size of one is big enough, that one is as reduced enough. So that is just the basic thing we want to know. There's a reduction at the cathode, then there's oxidation at the anode. Don't forget, oxidation means loss of electron, reduction means gain of electron. So a dry cell is a galvanized cell with the electrolyte contained in a thickened with starch, in a paste thickened with starch. So we talk about Daniell cell here as example of a wet cell, simply because it contains solution as electrolyte. But in this case now, when we have a Daniell a dry cell, instead of electrolyte to be in solution form, it is in a paste form. That makes it dry, and it is much more portable than what is called Daniell cell. The first dry cell invented by French chemist, that is Georges Leclanche, in 1866. That's what's called Leclanche cell. An example of that Leclanche cell is all those batteries that we use to light our bulbs, torch light, and some other applications like that. That's an example of a dry cell. So if you have many cells now connected together, that's what is called battery. Physics should be able to physics teachers will be able to clarify that for you. So when you now have them together, either in series or in parallel, depending on how they will explain to you in physics, that's what's called a battery. A cell is just a single one. When you have two or more, that is what is called a battery. So now, the voltage of a set of cells connected in series is the sum of the voltages of the individual cells. And like I said, physics will take care of that. So when you have battery that is not discharging again, that is not producing any current again, it means the power inside the battery, the current, the electron that is flowing inside the battery is used up. It's a exhaust state in the reactant. Don't forget, the reactant cannot be going on and on like that. So there's going to be a time when the number of replaceable ions will be exhausted. At that particular point, the battery stops working. And when the battery stops working, what can we do? It depends on the type of battery. Is it rechargeable or not? If it's rechargeable, then we recharge it. If it's not rechargeable, then we buy another one. So example of one that is not rechargeable is the Leclanche cell. All those small batteries that we use to light up our torch lights at home. All those are primary cells. Once they are used up, then they cannot be recovered again. Another one is the secondary cell, that is alkaline cell battery. All those ones are more sophisticated. So when they are used up, we charge them later. Example of the battery of our phones, the battery of our rechargeable lantern, and other things. They are all dry cells. So if they are exhausted, then we power them by recharging them. So now, let's introduce what is called cell potential. What makes this battery to be working? We have been explaining this is the type of battery, this is what is inside the battery, this is what is being used for. Now, potential. How long can battery work? What makes it work? Now, potential, as that name implies, potential ability. So as we know, there's a chemical change that takes place in galvanic cell. These are accompanied by changes in potential energy. Don't forget, these energy batteries, these cells that we are talking about, convert chemical energy from the battery and from the solution of the salt into electrical energy, that is the flow of electrons. So as we have flow of water that can be used to do some work, when we have flow of water, like the water is coming from the up to the downhill with a very high potential, from the high to the up, the very high potential with respect to the down, the force, the gravitational potential energy, the difference between the up and the down part, the bottom part of where the water is coming, can be used for some applications. Example, we can use it to drive our turbines, to drive our motors. So what we're trying to say is that when there is imbalance in the potential of the starting flow and the ending flow, there's going to be a change in potential, then we can harness that to produce some energies. So the same thing applicable here now in cells. When during flow of electron from the anode to the cathode, if there is change in potential between the anode and the cathode, then we can use that cell for application. Example of an application we can use the cell to do is to light or tune up our bulb. If there's no change in potential, then we can't do anything. Example is this: we said if we let me give another a familiar example. When we have a lemon, we have a lemon in a container. We have two electrodes. If you connect bulb to it, it will light up our bulb. Now, that is if we have two different electrodes. What if we have the same electrode, like let's say copper, zinc? I mean the anode and cathode are the same, like copper and copper. Are we going to have anything? No, we are not going to have anything of such, simply because the potential are the same. There's not going to be any change in potential, then electron will not flow. When the electron is not flowing, then there is nothing like change, nothing like electric current. So in effect, what we are trying to say is this: electrons spontaneously flow from a position of higher potential energy, that is the anode, that is when the concentration of electron is high, to a position of lower potential energy, that is the cathode. Then this movement of electron can do work such as lighting a bulb or turning a motor. So the difference between this potential energy now at the cathode and the anode is called electron potential. That electric potential is called cell voltage. We're talking about cell here, or voltage, V, capital letter V. Then the unit is small letter v, measured in volts with the head of voltmeter. So for current to flow, the potential must be different between the two electrodes. So if you set up a particular cell now, you want that cell to work, then the electrode you need to use must be different, so as to create a potential that is not balanced between the two. If there is balance of potential, then nothing will flow. This small table that we are seeing here is the short table of standard potential. This is not the head of the table. There are various tables in various textbooks. You can visit your textbooks to see there are compilation of potential. These are called reduction potential with respect to hydrogen, because you can't measure potential of half cell independently. No, you have to measure the you have to measure relative potential, then you now compare with the other one, so as to be able to get this potential of half cell reaction. What I am saying is this: if you have sodium hydroxide and hydrogen chloride reacting together, yes, of course, there is redox. So oxidation half equation is there, reduction as half equation is there. So to measure oxidation or reduction, you can't measure them independently. You have to measure it with respect to the hydrogen. That is why the potential of hydrogen is given as 0. So these are relative potential of each of them. So if you look up, you study this table very well, you are going to see that those atoms, those elements that has very high tendency to lose electrons, whose reduction is very, very high, you see the value very, very high. But the one that are not likely to lose electron, that is when you see low. I mean that are not likely to gain electron. You see it here, because we are talking about reduction. Reduction is the loss of electron. Anyone that loses electron faster, has lower potential. Anyone that gains has higher potential. That is what we are saying here. And since hydrogen is indifferent, so that's why it is 0 here. So the potential given above is the relative potential of each half cell potential to that of hydrogen electrode as standard condition. Then what are the standard conditions? For concentration is 1 mole per liter. If it's a liquid, if it is a gas, it's 1 atmosphere or 101.3 kilopascal, and the temperature is 298 Kelvin or 25 degrees Celsius. So let's now do some examples to see if we really understand what we are talking about. So if we want to calculate the standard cell potential, because this aspect is where we are taking this lecture today, we need to be very, very careful with it. So I will introduce two methods to calculate it. The first one is this one, the subtraction method. The E of the cathode minus E of the anode. Please don't make that mistake. Cathode first, then anode. If you are to calculate the standard potential of a Daniell cell, in a Daniell cell, you know your electrodes, copper and zinc. So now it is your duty to know which one is oxidation, which one is reduction, which one is cathode, which one is anode. Don't forget, copper is the cathode, zinc is the anode. So you look back to your table here. This is the copper is 0.342. Then what is zinc? Minus 0.762. Then just come and write it here. I mean for reduction now. 0.342 here for copper. That is the cathode. Then here is the anode. Then you use these values. Then you put it here. You see it's a 1.104 volts. It is simple, but if assume now that you misplace this, let's say you put is a minus 0.762 minus 0.324, you get the negative of that. So it means this cell has negative potential, which is not, because all primary cells have positive potential. So that is just by the way. The second method is this method, when we had reduction plus oxidation. Let me explain this reduction and oxidation before we go. I said in the table I showed, the potential, the values we saw on that table is for the reduction of equation. So if you want to transform anyone, like oxidation, because hydrogen was used as a standard, so anyone that is reactive than hydrogen, take it as reduction. Anyone that hydrogen is more reactive than it, take it as oxidation. So if you are now considering, let's say, sodium and fluorine now, hydrogen is not there, it's not there again, because if you are considering hydrogen, that is when you use this value. If you are considering this aluminium and let's say bromine now, bromine is always there. So if you want to count aluminium now, you have to transform this, because it is oxidation now and it is reduction. If you want to get the oxidation of it, you want to transform this. Anyone that is easier for you is what to use. I'm just trying to explain the other one. So you can have the oxidation potential instead of reduction potential. So the oxidation potential now, out of the two, which one is it should be oxidation. This is anode, oxidation. So instead of the negative that is there, you put the positive, because oxidation is your directly opposite of reduction. So you add them together, so you have the same value as you have it when you use the other formula. So another example is calculate the standard cell potential for the galvanic cell in which the following reaction occur. We have a reaction with sodium and water to form sodium hydroxide and hydrogen. So the first thing you are going to do, I just try to explain this example in more detail than the first one, because this one is more involving than the first one. Not that it's difficult, but I think students will complain that it's more difficult than the first one. The first one is easy, pretty easy, simple. So write the equation in ionic form to identify the half reactions, and we have written it in ionic form. Sodium has lost electron to become this, then this one has gained an electron to become this. So after that one, you just split them. So if you split them, write the oxidation and reduction half equations. The one that loses electron is the oxidation, that is the anode. The one that gains is the reduction, that is the cathode. So now after that one, now go to your table, then locate the reduction potential for sodium is minus 2.77, then for the water is minus 0.028. So if you if you subtract anode from the cathode, what do you have? You still have positive. So you can still use the other formula to confirm if you want to confirm, but I bet you are still going to get the same answer, because if you do that, this anode is where you transform to be positive now. So now it's now be 2.711 minus 0.828, and it's going to be the same thing as this one. So this is what we have for today, but before we go, let us have some quick recap of what we have done. The flow of electrons constitutes electric current. We have known that one before. An example of photovoltaic cell, electrochemical cells, which could be Leclanché or Daniell cell. Leclanché is the dry cell, Daniell cell is the wet cell. And I said the difference between the wet and dry is the nature of the electrolyte. In the wet cell, we have electrolyte to be in solution form. In dry cell, instead of solution, it is in a paste form. That is it. So cell potential calculated by considering the reduction potential of cell equations. That is what we have for today. Don't forget to share and like our video. We are moving to the next part, a next subsection of chemistry now. That is the concept of metals. So we are going to take all these common metals one after the other. Like the group 1, take maybe 2 elements from group 1, take from group 2, from group 3. Then we now go to transition metals. Then we study their compounds. May God just be with us and make us to be healthy. Thank you for listening. Don't forget to share and like our video. Thank you very much.